Hello everyone, this is Brock Skaggs. I'm going to make this video where we'll examine a crank rocker mechanism, and specifically we're going to perform a velocity analysis. And so our setup here is that we know the position of the mechanism at this given instant in time, and that's what you can see before you here on the left hand side, where our crank is link AB here on the left, we've got the coupler in the middle, and our rocker is link CD here on the right hand side. And so at this instant in time, the crank is 30 degrees above the positive x-axis, if you will. And so also at this instant in time, we know that the angular velocity of the crank is going counterclockwise at 60 RPMs. And so the question is, at this instant, if the crank is rotating counterclockwise at 60 RPMs, what is the angular velocity of the rocker, link CD here on the right-hand side? And so there's a few different ways we could use to solve this. The way we'll look at is a method involving relative velocities. And we'll go for a largely analytical calculation. And so the first thing I'm going to do is I'm going to make a very simplified version of this sketch down here so we can talk about some of the vectors that we'll be dealing with. And so I'll get my pen out to zoom in here and go to work. And so there is the crank. Our coupler kind of walks down here. I guess imagine that's a straight line. And then here is the rocker over here. And the fixed pin connection. And so what do we know about this? Well, we know that this link, the crank on the left-hand side here, is rotating counterclockwise, so some omega 2 value here, that it happens to be 60 RPMs at this given instant. Well, that would allow us to figure out the linear velocity of this point here. And so I'll draw it just like so. We know the direction of it has to be in agreement with the omega 2 vector, so if this thing's spinning counterclockwise, it would make sense that the velocity of this point at this given instant is moving up and to the left. And also we know that it's going to be perpendicular to that radial line that I've created to represent the crank itself there. And so that nice 90-degree angle there is that relationship. Another way of thinking about it, besides being perpendicular to this radial line, is that basically point B is going to trace out a nice circular path as the crank rotates about its fixed pivot point, and this velocity is going to be tangential to that circular path. And so that gets velocity B. Another velocity that we'll try to find is the velocity of C. And so I'll draw that right here. Our points were A here, B here, C, and D. And so we're looking for the linear velocity of point C. The big reason we want to find the linear velocity of point C is because if I know the linear velocity of this point, and the length of the rocker, which is given, then I can figure out the angular velocity of the rocker from that. And so this will be one of our main steps in the solution path. Now, since we're using a relative velocity method of solution, the relative velocity equation that I'm thinking of looks like this. So we've got the velocity of C is equal to the velocity of B plus the velocity of C relative to B here. And this should be good for this situation, and specifically I'm looking at applying this to points that are on the coupler. And so coupler, remember that's the middle member that's connecting the crank on the left-hand side to the rocker on the right-hand side. And so at this point I'm thinking of points B and C lying at the ends of the coupler itself. And so we've talked about the two terms so far, velocity of C and velocity of B, but what's this relative term all about? Well, the relative term C relative to B is basically if you were on B looking at C, what would it look like it's doing? And so one thing to remember about this is that there's a specific direction here. If you look at some books, they'll represent this as an actual cross product happening for this term. And since there is a cross product, one of the things you know that comes out of a cross product is a vector that is perpendicular or orthogonal to the two other vectors. And so in this case, the way you can think about it is that if points B and C lie on the same rigid body or the same length, which here there is the coupler, then if I drew a line connecting points B and C, then the direction of this relative velocity vector would be perpendicular to that given line. And so in this case, even though it's a little squiggly because of my somewhat bad drawing here, this is a line connecting points B and C, and I know that this relative velocity vector is going to be perpendicular to it. And so for that, I'll just draw down into the left at this point in time. And so there's the velocity of C relative to B. And again, I know the direction has to be perpendicular here. And then this velocity C is going to be perpendicular to the radial line here, which is symbolizing the rocker. And so at this point, I've got one vector that I know everything about, the velocity vector B here. At the top, I know both direction and magnitude. And I've got two vectors here that I only know the directions. At this point, I can't tell you what their magnitudes are. I think I can have it in the right spot here, but I can't for sure tell you I've even drawn them in the correct direction in terms of their sense either. It could be possible that, say, the velocity of C relative to B vector actually points upward and to the right instead of down and to the left there, because again, the only thing I know by definition is that it's got to be perpendicular to this radial line, or to not the radial line, but to the line drawn between points B and C. And so the idea here we'll work through the vector equation here in order to solve for the magnitude of velocity C, and then from velocity of C's magnitude we can come up with the angular velocity of the rocker length. And so with that being said, we have a little bit of work to do before we can use the vectors here. And so I'll scoot over here to the right and start working through that vector math. And so the first thing I'm going to think, well, I've got a vector v sub b. And so there's my vector, there's the velocity of point B. And so I mentioned earlier that we know everything there is to know about v sub b, which means direction as well as magnitude. As far as magnitude goes, I'm thinking r omega. I've got a crank, it's just in pure rotation about a fixed point, so it's the opposite end of the crank, and so we should be able to take the length of the crank times the angular velocity of the crank in order to come up with the magnitude of that vector. We've got a little bit of work to do first. Right now the angular velocity of the vector is at 60 RPMs, and so I don't really need it at 60 RPMs, but I need to convert that, and so we're looking at omega 2 here. And it's currently at 60 revolutions per minute, and I need to get this to radians per unit time. Here I'll use radians per second, and so here we have 2 pi radians for every 1 second, or excuse me, for every 1 revolution, and then there's 1 minute for every 60 seconds. So we've got revolutions here and here, minutes here and here. And I end up with 2 pi radians per second. And so here's our omega 2 value. And now we're ready to calculate the magnitude of the velocity of B. And so, alright, the magnitude of V sub B. Here in my mind I'm thinking r omega, just the way I've used to seeing that formula, except for here instead of r we have the length of the crank, and so L2, which has a value of 3 times r omega 2. And so here I'll just write L2 times omega 2, which we said was 3 inches, times the 2 pi radians per second, which yields 6 pi inches per second. So now that I know the magnitude, I need to work on the direction. And so the direction, I'm given up here that the angle that the crank's making with the positive x-axis is 30 degrees. And so from that I should be able to work out the angle of this vector. The angle of the vector is pointed, I should say. And so here what I'll do is make a very simple sketch this diagonal line representing the crank. Draw a horizontal line here with construction. There's a 30-degree incline. I'll draw my vector in here. That red arrow is the vector velocity of B. We know that it is perpendicular to the crank's line there. And so, for instance, I can calculate this value to be 60 degrees there, just 90 minus 30. And so now that I know the direction that it makes with the negative x-axis, I should be able to break it into I and j components. And so I'll do that right here, and I'll say the velocity of B. We first think, okay, it's pointed in the second quadrant, so negative I and positive j. That would be negative 6 pi times the cosine of 60 degrees I, and then plus 6 pi times the sine of 60 degrees j. And so take a step back and think, yes, at this point I have fully described the velocity vector of point B, the linear velocity there. And so what that means for us in terms of this equation is that I now have fully described this term. And so now I just have to describe two more before I can use the vector equation. And so I'll slide down here a little bit. And now we can work for, say, the velocity of C. And so here's some more vector work. And we're looking at the linear velocity of point C. And so point C here, if I knew the linear velocity of it already, I wouldn't have to go through this part of the problem. And so I don't know the magnitude of it. And so I will say, let's let the magnitude of the velocity of C equal v sub c, except now here we're leaving off the hat, and so I'm just thinking of this as the scalar magnitude associated with this vector. And so basically on the direction, or on the magnitude side, we're letting it be represented by a variable. What about the direction side? The direction side, remember we said we had a known direction here. And so part of this known direction would actually come from information that would be involved in a position or displacement analysis. Basically that same stuff could be read off from our layout here the way I've drawn it up graphically. And so in order to shorten the video here a little bit and focus just on velocity, I'm going to tell you, hey, this theta 4 value has already been found, and it is 102 degrees. And so now that I know that angle, I would be able to come up with the angle to describe the direction of the v sub c vector here. And so again, that green stuff could come from an analytical version of the position analysis, or I could have also done it graphically. And so this black line will represent the rocker. There's our v sub c vector. There's a horizontal line. I'm going to redraw that in green. And here is our theta 4. And so now we've got to work toward describing v sub c here. And so one thing we could do is figure out this angle here. Just call it lambda. This angle would be a 90 degrees. And then this angle over here, let's call it beta. We could then use to relate the I and j components. We could also even stop at calculating lambda and just know that the overall angle here from the positive x-axis is 90 plus lambda. And so here we can say our lambda character is 180 degrees minus theta 4. Just 180 degrees minus the 102 degrees. So that is 78 degrees here. Now let's go ahead and calculate beta. That would be 90 minus lambda. So 90 degrees here minus my 78 degrees gets us to 12 degrees for that value. And so now that I've got the direction ironed out, I can then write the vector v sub c in I and j components, which is using a scalar magnitude or scalar value to represent the magnitude. And so I'll do that right here. I've got the velocity of c is equal to, if I use beta, I'm going to be in the second quadrant here, so negative I, positive j. And so negative v sub c, no hat here, times the cosine of beta, which is 12 degrees I. And then I'd have plus v sub c times the sine of 12 degrees j here. And so now I've been able to describe this term, the v sub c, for my vector equation. So one more. I'll see if we can go through this fairly quickly. We've got the relative velocity vector. And so have another vector here. This is the velocity of c relative to b. Again, I don't know the magnitude for this one, and so we'll just let it be represented by a variable. And so we'll say let the magnitude of this vector equal the velocity of c relative to b without the hat this time. And now we would need some information from the position analysis. Just like last time, I'll go ahead and just tell you an angle to kind of speed this up a little bit. Say this angle here, we'll call it theta 3. I know is 67 degrees from some previous position-related work. And so now we need to be able to determine the direction. And so using that angle, draw a line here representing the coupler. Here is our theta 3, which is 67 degrees. We've got the relative velocity vector drawn perpendicular to this line and in this direction here. And so that was not a very good straight line. Here's a halfway decent straight line. We know this angle is 90 degrees. Alternate and ternary angles would tell me that this angle is also going to be theta 3 here. And so I should be able to come up with this value here. Let's call that beta again here, where this beta is going to be different than the beta above. Looks like that beta would equal 90 degrees minus theta 3. If we want to, we can call this beta 1 as a subscript. And so this beta 1 would be 90 degrees minus theta 3. So 90 degrees minus our 67 degrees gets us to 23 degrees. And so from this, we should be able to now characterize this relative velocity vector in terms of I and j components. And so we would say something like the velocity of c relative to b is equal to, here I've got something pointed in the third quadrant, so both negative I and j terms. And so I'll say something like negative vc relative to b times the cosine of 23 degrees I minus the velocity of c relative to b times the sine of 23 degrees j there. And so at this point, we are now ready to start looking at this vector equation over here, because at this point I've got all three of these characterized in terms of I and j components. And so we'll work on this down here. So now we're ready to basically look at our relative velocity equation. Relative velocity equation analysis. And so again, as a vector equation, we're saying that the velocity of c is equal to the velocity of b plus the velocity of c relative to b. And so this is the vector version of our equation. One thing we know is that if the relationship is true at the vector level, it also has to be true at the individual component levels. So I can write the same equation just looking at the I components and the same equation just looking at the j components. And what we'll need to do for this specific example is we'll basically need to be able to solve those resulting scalar equations simultaneously in order to come up with our desired magnitude of the velocity of c. And so with that, now I will write the equation just looking at the I components. And so first I've got to find the magnitude of the velocity of c. not, excuse me, not the magnitude, but just the I component of it. And so here I have it as negative VC times the cosine of 12. See if I can just grab these. And so bring that down here. That was the I component for V sub C. Go ahead and put the equals in here. This is equal to. Now I need the I component of the velocity of B. That's right up here. And so place this in here. And then I need the I component of the velocity of C relative to B, which is what we wrote right here. And so this forms the vector equation, except for only looking at the horizontal components. And so notice at this point I've got a scalar-based equation, but I've only got one equation and two unknowns, V sub C and VC relative to B. And so I can't solve for either of those directly at this point, so now I will need to write the same equation except for only looking at the J components. And so do the same thing just looking at the J components here. And so I'll start grabbing stuff from my previous work. Here was our velocity C part. Go ahead and put our equal sign in. And then the velocity of B was up here, just again looking at the J component. This goes here. And finally the velocity of C relative to B right here. Alright, and so at this point, take a step back and see what you've created. Here we've got a system of two equations, the I and J equations here, and we have two unknowns, the V sub C and VC relative to B. And so now we just need to solve these simultaneously. And so we could do this by hand, but instead of doing it by hand, let's see if I can use Sage in order to help myself out here. And so here, I'll go ahead and create a Sage worksheet. And then as soon as this gets loaded up, I will bring it over. Here we go. And so here I just created a simple worksheet inside of Sage Math Cloud. You're seeing the interface before you. A few things I'm going to have to do is I'm going to have to define symbolic variables to represent V sub C and VC relative to B. And so I'll just put var V underscore C and V underscore CB. Another thing I'm going to do is I'm going to create a custom function. It expects the arguments for sine and cosine to be in radians, and I have them in degrees. And so I'll just define a function called radians that I'll pass in a parameter z, and it's going to return z times pi over 180. And so what that should allow me to do is basically just wrap my angles in this radians function, and it'll convert them automatically from degrees to radians. At this point, I need to basically store my I and J equations, and so I'll just say I underscore equation, EQN for short, and I'll just type out the equation at this point. So I've got negative V underscore C times the sine, and remember I've got to wrap it in radians, so the sine of the radians of 12, because it's really the sine of 12 degrees. And I'll put the double equals here because it's not an assignment. And the next term is negative 6 pi times the cosine of 60 degrees, so it's negative 6 times pi times the cosine. Again, wrap the 60 in radians for degrees there. And then minus V underscore CB times the cosine of 23 degrees. And so there is my I equation, and now for the J equation. And for J, VC times the sine of radians of 12. It looks like I messed up in the I. Yes, the I should be cosine here. There we go. accidentally glanced at the wrong one. And then equals 6 pi times the sine is 60. And so double equals here because we're not talking about an assignment. 6 pi times the sine of 60, excuse me. And then last we have this term here, negative VC relative to B times the sine of 23 degrees. Negative V underscore CB times the sine of 23 degrees. And again, we're converting everything to radians. I'll hit Shift Enter. That evaluates the cells. Looks like it's stored fine. And then I'll just take 1 second to make sure that these all match up. Excuse me, before moving on. And I think we're in good shape. And so now I just need to have Sage solve this system of equations for the results. And so we'll just say I'm going to have a dictionary solution come out of the solve command. Inside of solve I'll use square brackets here and list the equations. So I equation and J equation, the two equations we defined before. Comma, what are we solving for? We're solving for V underscore C and V underscore CB. And I'm going to put one optional parameter in here that the solution underscore dict needs to be true, and I'll grab the first element in the list. So what that should do if I show the dictionary solution is provide us with the values for V sub C and VC relative to B. At this point you can see the kind of exact solutions here, which aren't really as useful as one would think, because hey, I would like to actually know a number here instead of the fraction. And so here I'll just say print V underscore C, and then we'll see if we can first round the value. And so I'll grab from the dictionary solution V underscore C. I want to round it to say 2 decimal places, then cast it as a string, and then just put something nice at the end like inches per second there. And so we can see that the VC, when they evaluate this fraction, it ends up being 32.62, and the units will be inches per second there. VC relative to B, even though it's not deeded directly for what we're asking for, we can see that's 24.42 inches per second. And so what this gives us is the magnitudes of our two vectors that we did not know the magnitudes before, VCB and VC. Also, they're both positive, so we assumed the correct directions here. And so since I've got this value from Sage, now I'm just one small step away from determining the angular velocity of the rocker. And I'm interested in this value right here, that the velocity of C is 32.62 inches per second. And so here we'll say from Sage, the velocity of C, as far as the magnitude of that vector, was 32.62 inches per second. And so now that we know the magnitude of this vector here, the velocity of C, we can relate it back to the angular velocity of the rocker link. And so just to draw a picture emphasizing the angular velocity of the rocker link, we've got a fixed pivot connection or pin joint here. We've got the rocker lying somewhere like this. We now know the velocity of C, which is going in this direction. And so that means that we've got the angular velocity of this length, we'll call it omega 4, is going in this direction, and we should be able to come up with the magnitude of it. Just looking at the magnitudes of these vectors, you would say the velocity of C is equal to L4, which this length here would be L4 between these two pin joints, times omega 4. Again, since we just have a fixed pin joint here, and this link is just under pure circular motion. And so we can say omega 4 is equal to VC over L4, and VC was our 32.62 inches per second. And L4 is up at the top here, 6 inches. So this over 6 inches. And give me 1 second to grab my calculator. 32.62 divided by 6, roughly 5.44 radians per second is the unit there. So 5.44 radians per second, rotating in the clockwise direction. And so 5.44 radians per second, just to give you a feel, we can convert that pretty easily to degrees per second. What would you have? 180 degrees divided by pi radians. So I'll just take this value of my calculator to multiply by 180 divided by pi. Ends up right around 311.5 degrees per second there, going clockwise. Would be another way to put the results here. Just to show us a little bit more, here is the same mechanism. I went ahead and ran it inside of SolidWorks. There's the motion of it. The vector you're seeing growing and shrinking there is the linear velocity of point C. But since we know that the angular velocity of the crank, or excuse me, the rocker, the blue link, should start off at roughly 311 degrees per second. Here is the plot of that, the rocker angular velocity, and if I get here close to the 0 point, you can see at 0.01 seconds it's at 308 degrees per second, a negative there because it's moving in the clockwise direction there. And so that's really good agreement with our analytical calculation there. Our analytical is probably a little bit off, partially due to the fact that my angles here that I got from my position analysis, 67 degrees and 102 degrees. Here I just rounded it to the nearest degree, if you will. And so this has been a successful trip. We were basically able to figure out the angular velocity of the rocker for the mechanism itself. Again, basically we walked through a relative velocity style solution, did it mainly analytically in order to come up with that value. And so hopefully this helps you with your velocity calculations. Thank you for watching the video.